Good afternoon to our viewers. On behalf of School of Engineering and Technology, we welcome to our students those who are attending this interactive EduSet lecture session. Today's topic is second law of thermodynamics and its application. This topic is from Engineering Thermodynamics, and Engineering Thermodynamics is the course which is being offered to our BTech Civil as well as BTech Mechanical Engineering. So let us discuss today about the second law of thermodynamics and its applications. Before discussing second law of thermodynamics, let us touch upon the basic definitions for system, surrounding, control mass and control volume. And we will also discuss in brief about the first law of thermodynamics. Then we will go for the second law of thermodynamics and its application. See, any identifiable matter which is to be studied for thermodynamics properties is known as system. Say for example, you consider a piston cylinder arrangement and you keep some gas inside the cylinder. So the gas we can consider as a system, and anything outside the system is known as surrounding, and the system is being surrounded by a boundary. And for this system there may be heat interaction, there may be work interaction between system and surroundings, but the mass within the system is constant. There will be no mass transfer from system to surroundings. And the system plus surrounding, we call it universe. So there is also another very important concept that is known as the control volume. But here we consider a confined space, and here also there is a boundary, and when the matter enters in the control volume, we will study about its thermodynamic properties. But there is a difference between control volume and control mass. For control volume, there may be work interaction between surrounding and control volume. There is a heat interactions, and there is also mass interactions. The meaning of mass interaction is there may be mass entering into the control volume, and there also possibility for going out of mass from the control volume. Now, many systems are most conveniently analyzed as a system fixed in space, which permits mass to cross the boundaries. Such system is defined to be control volume. Say for example, turbine. Inside the turbine, the blade rotates and we get the output from the turbine, but the mass may enter into the turbine, and the mass also may go out from the turbine. We will discuss about the turbine or thermo electric power plant in detail in due course of time. See, for system there may be work transfer, there may be heat interactions for the system, but the mass within the system is constant. But as far control volume is concerned, then there may be work interaction, there may be heat interactions, and there may be also mass interactions. And when you think of a very important system that is known as the isolated system, in that case no interaction is permissible. Let us discuss very briefly about the first law of thermodynamics. The first law of thermodynamics speaks about the conservation of energy. As we all know, for the conservation of energy, energy cannot be created, not destroyed, but the total energy is always conserved, and there may be conversion of energy from one form to the other. A process is cyclic if the initial and final state of the system executing the process are identical. Why we are discussing about the cyclic process? Because it will be easier to understand the first law of thermodynamics for a cyclic process. When a system executes a cyclic process, the net work is proportional to the net heat. Mathematically, we can express it as integral of del W is equal to J integral of del Q. Here del W is the net change in work and del Q is the net change in heat supplied, and here we have introduced a term that is J. Here we are converting the heat unit into work unit. Now we had already discussed about the first law of thermodynamics for the cyclic process. Now let us see that what will be the expression for the first law of thermodynamics for the non-cyclic process. For the non-cyclic process, here you see that the expression is Q minus W is equal to delta E. Here Q is the heat supplied, W is the work done either by the system or on the system, and delta E is the change in energy. So delta E denotes the increase in the magnitude of energy E during the process. The analysis of the first law of thermodynamics speaks about different conditions of the process. You take a very simple example. What will be the expression for the first law of thermodynamics for the control volume process? So for the control volume process means, for the constant volume process, the volume is constant, so there is no work done. So delta W term will be 0. So finally we will get the expression for the first law of thermodynamics for constant volume process is du is equal to delta Q. Here you see that we are using D for U. The reason behind this that the U is the energy, it is a point function, while Q is the heat, and heat and work are the path function. That's why we are using delta for Q and D for U. Here we are considering a control volume and see the expression for the conservation of mass for this control volume. So this is the boundary for this control volume. As we already mentioned that for the control volume, mass may enter inside the control volume, mass may also go out from the control volume. So in this case, m dot in is the rate of mass transfer into the control volume, and m dot out is the rate of mass transfer going out from this control volume, and mCv is the mass within the control volume. So if we consider the rate of change of mass within the control volume, that is del T of mCv is equal to m dot in minus m dot out, and the expression for this for steady state condition, as you all know that for a steady state condition the property will be invariant with time. So del T of mCv will be 0 in that case for a steady state condition. Finally we get for a steady state condition is m dot in is equal to m dot out. That means the rate of mass entering into the control volume has to be equal to the rate of mass going out from this control volume. Now let us discuss about the conservation of energy, that is the first law of thermodynamics in case of control volume. So here also we have considered as control volume and is the boundary, and in this case E dot in, that is rate of energy entering into the control volume, E dot out is the rate of energy going out from this control volume, and W dot is the rate of doing work by the control volume, and Q dot Cv is the net rate of heat supplied into the control volume. So if we write down the expression for conservation of energy, that is dou T of ECV, that is the rate of change of energy inside this control volume, is equal to E dot net plus Q dot Cv minus W dot. As we have already discussed, for the steady state condition, any property of the system will be invariant with time, or we can say that any property for a steady state will be independent of time. In that case, that rate of change of property will be 0. So For a steady state condition, E dot net plus Q dot CV minus W dot is equal to 0. Now, before discussing about the second law of thermodynamics, let us try to understand different components for steam power plant. My dear friend, you know very well the energy scenario in India. Around 65% of the power generation is being carried out by thermal power plant, and around 28% of power generation has been carried out by hydroelectric power plant, and only 2% power generation is being carried out by nuclear power plant, and the remaining around 7% of the total energy is being generated by non-conventional energy like wind energy, solar energy, and tidal energy. So, the majority of the power generation has been done or carried out with the help of steam power plant. Now, see, there are four main components of steam power plant: the boiler, turbine, condenser, and pump. See, the boiler, the working substance which is being used for this steam power plant is water, and the heat is being supplied onto the water, and water is getting steam. This superheated steam is entering into the turbine. It is doing shaft work, WT. So, WT is work done by the turbine. Then the low pressure steam is being sent to the condenser, and here the heat is being rejected Q2 to the surrounding or outside air, or any kind of say heat exchanging is taking place in the condenser. Simply we can say Q2 is heat rejected to the surrounding. After that, the working fluid, that is water, will be condensed into water, and the pump is required for pumping it again to the boiler at high pressure. And again here it cycle completes. Again we are heating by burning of fuel inside the boiler and making the water into steam, and again the high pressure steam is entering into the turbine, and that's why the whole cyclic process is going on. In this case, you see, we have considered a boundary, and here inside this boundary there is heat interactions and there is work interactions. So in this case, Q1 is the heat supplied to the working substance, and Q2 is heat going out from the working substance to the surrounding, and WT is the work done by the system is positive, and work done on the system is WP. So since it is a cyclic process, so we can say integral of del Q is equal to integral of del W. So if we write down the mathematical expression for the first law of thermodynamics in case of steam power plant, we can write down that summation of work is equal to the summation of heat. My dear friend, please be careful while writing the expression for W or Q. The sign convention says that any work done by the system is positive, so WT is positive, and any work done on the system is negative, so WP is negative. Heat input, heat going out from the system, that is Q2, is negative, and heat going in into the system, that is Q1, is positive. So with this sign convention, if we write down the expression for first law of thermodynamics, we can write this expression, that is Q1 plus minus Q2 is equal to WT plus minus WP. Here you see we have explicitly considered the sign convention, because Q2 we have considered negative because heat is going out from the system, and WP is the work done on the system, that's why it's negative. After rearranging, we are getting Q1 minus Q2 is equal to WT minus WP. Now if we consider the thermal efficiency, as we all know that the definition of efficiency is output by input. What is the net output? That is Wt minus Wp, and the net input into the system is Q1, that is heat supplied to the system. So the efficiency is equal to Q1 minus Q2 by Q1. Finally we get the efficiency equal to 1 minus Q2 by Q1. So we have already discussed about the thermal power plant different components, and now the time has come to discuss about the working principle of refrigerator. In the refrigerator there are 4 components. One is condenser, second one is compressor, third one is evaporator, and the expansion device. Now see that at a very low pressure and low temperature working fluid, here the working fluid is freon gas or refrigerant. We call it refrigerant. There are different types of refrigerant like R11, R12, and these are the chlorofluorocarbon, and different commercially named refrigerants are available like R11, R12, R22, and like that. So low pressure, low temperature refrigerant entering into the evaporator, and here it is taking heat from the confined space. Virtually we can say that in the confined space we are keeping the vegetables which is to be cooled in a domestic refrigerator. So here Q2, he is taking out the heat from the confined space. After that it is entering into the compressor, and work is done on the system, and the temperature and pressure is again increased because of the work done on the system, that is within the compressor, that is WC is the work done onto the system, and temperature and pressure increases. After that the working fluid, that is refrigerant, is entering into the condenser. Here the temperature and pressures are very high, and definitely since the heat is to be rejected to the surrounding, so definitely the temperature of the refrigerant has to be very high than the temperature of the surrounding, otherwise heat will not flow. We all know that heat will always flow from the high temperature body to a low temperature body. After that the high pressure and high temperature refrigerant is entering into the expansion device, and this we use a thermostatic valve. When it is passing through the thermostatic valve, again the pressure and temperature decreases, and after that it is again entering into the evaporator. You see that if we consider a boundary, system boundary, and here there is a heat interactions and work interactions. So heat is going out from the system to the surrounding, that is Q1, and heat is going in from the surrounding to the system Q2, and there is work done on the system, that is WC. So in this case Q1 will be negative because heat is going out from the system to the surrounding. Work is done onto the system, so WC obviously it will be negative, and Q2 will be positive. First of all, let us write down the expression for the first law of thermodynamics for the refrigerator. Here you see that summation of Q is equal to summation of W, that is minus Q1 plus Q2 is equal to minus WC. So Q1 minus Q2 is equal to WC. In this case we write a very important parameter that is known as coefficient of performance, and coefficient of performance means the meaning is similar to the efficiency of a heat engine, that is defined as the net refrigerant effect by the work done. That means what we are getting divided by what we are paying. In this case our main intention is to heat extracted from the confined space, that is Q2, divided by WC is work done on the system. So coefficient of refrigerant will be Q2 divided by Q1 minus Q2. One very important device is there, we call it heat pump. So heat pump is basically pumping heat to the system, and that is defined as Q1 by WC, and if we do little algebra then we can find out the coefficient of heat pump will be equal to 1 plus coefficient of refrigerator. Now let us talk about heat engine. There are two kinds of heat engine we will discuss over here. One is direct heat engine, second one is reversed heat engine. In the direct heat engine, Q1 is the heat taking from the source. The source is always high temperature, that is T1 is the temperature of the source, T2 is the temperature of sink. Here that Q1 is the heat taken from the source, and E denotes for engine, the direct heat engine, and work is done by the engine, and Q2 is the heat rejected to the to the sink. Here that Q1 is the heat extracted from the source, that means engine is getting heat from the source, that is Q1, and W is the work done by the engine, and Q2 is the heat rejected to the sink, and sink temperature is T2, and T1 is always greater than T2. And this is the reversed heat engine. In this case, work is done on the system, and Q2 is the heat extracted from the sink, and Q1 is the heat delivered to the source. But here we call it reverse engine because you see that directions is reverse. So work done by the system is work done on the system. And here for direct heat engine, Q2 is the heat rejected to the source, but in the reverse heat engine, Q2 is the heat taken away from the sink. Here you see, while discussing the second law of thermodynamics, the second law of thermodynamics basically we can define second law of thermodynamics with the help of our experience. Here you see there are two important statements which define second law of thermodynamics. One is Kelvin-Planck statement, and second one is the Clausius statement. The Kelvin-Planck statement related to the heat engine, direct heat engine, and the Clausius statement relates to the reversed heat engine. So the Kelvin-Planck statement, it says that it is impossible for a device operating in a thermodynamic cycle to produce work while having heat interaction with a system at fixed temperature. So in this case, for this case, a device, say there is one engine and it is taking Q1 the heat from the source, and the whole heat, that is Q1, is being transformed into work. But basically in practical it is impossible. We cannot get any engine which takes continuously heat Q1 from source and converts 100% to work. That means in this case, if you see that if you calculate the efficiency of the engine is output by input. Here output is W and input is Q1. So the efficiency of this engine will be output by input, that is W by Q1. Since W and Q1 are equal in this case, so the efficiency is 100%, but in reality it is impossible. So Kelvin-Planck statement is one of the statement of the second law of thermodynamics. So we will discuss that how it is possible for any reversed engine or direct engine for this case. Second one is the Clausius statement. Clausius statement says that it is impossible for any device operating in a thermodynamic cycle to accomplish as its sole effect the transfer of heat from a low temperature region to a high temperature region. Here you see that Q1 in this diagram, Q is the heat taken from the sink, and this reversed engine without doing any work, that the same heat is being transferred to the source. In this case you see, if we apply the first law of thermodynamics, it is not violating, because the first law of thermodynamics speaks about the conservation of energy. In this case, if you apply first law of thermodynamics, this is satisfying, but in reality this process is impossible. So the cases in which we can apply very well the first law of thermodynamics, but in reality that process is impossible. You see the previous case, that Kelvin-Planck statement. In this case also there is a validity of the first law of thermodynamics, because it really speaks about the conservation of energy. That means Q1 is equal to W. So summation of Q is equal to summation of W. For this case there is no violation of first law of thermodynamics, but in reality this process is impossible. Then we come to the second law of thermodynamics, and second law of thermodynamics basically comes from through experience. There is no, as such, there is no proof for the second law of thermodynamics. Basically it talks about these two statements. One is Kelvin-Planck statement and another one is Clausius statement. One very important for the applications of second law of thermodynamics, these two different statements we had already discussed in detail, that is Kelvin-Planck statement and Clausius statement, and these two statements are interrelated. What do we mean by interrelated? That means if there is any violation of Kelvin-Planck statement, there will be automatically violation of the Clausius statement. If there is a violation of Clausius statement for any process, there will be also violation for Kelvin-Planck statement. Let us see with the help of diagram why it is so. In this case, you see that we are talking about the equivalence of Kelvin-Planck and Clausius statement. So in this case we will discuss, if there is a violation for Clausius statement, then there will also be violation of Kelvin-Planck statement. So in this case T1 is the temperature of the source, T2 is the temperature of sink, and here we are considering two heat engine. One is direct heat engine, another one is reverse heat engine. For the reverse heat engine there is a violation of Clausius statement. In this case you see that Q2 is the heat received from the sink, that is low temperature region, whose temperature is T2, and the heat thus is rejected to the source. Here the heat is being transferred from a low temperature to a high temperature region, and of course there is a violation of Clausius statement. But when you think of the direct heat engine, in this case the same heat Q1 which is being delivered by the reverse heat engine to the source, we are taking the same heat Q1 to run this direct heat engine, and in this case W is the work done by the engine and Q dust is the heat rejected to the sink. In this case you see from the diagram that there is no violation for the Kelvin-Planck statement, because for the Kelvin-Planck statement we need a source, we need a sink, and there will be work done by the direct heat engine. But there is a violation of Clausius statement. Now let us see that this whole process will not be possible. In this case there will be also violation for Kelvin-Planck statement. We are considering one system boundary. Here this is the system, and you see that if we write down the expression for the conservation of energy, that is the first law of thermodynamics, we can write the expression for the first law of thermodynamics, that is Q1 is equal to Q2. And here see that Q1, that is the heat into the engine, direct engine, and W is the work done, and Q dash is the heat rejected to the sink. In this case that we can write Q1 will be equal to W plus Q2 dash, and W will be Q1 minus Q2 dash. So W is equal to Q1 minus Q2 dash. Now you see that the expression for efficiency is equal to output by input. So in this case, that W is the work done by the system and Q is the net input to the system. Here net input to the system is nothing but Q2 minus Q2 dash. But Q1 is equal to Q2. So Q and W, these are coming same. So efficiency is 100%, and that is not possible for any device. So in this case, if there is a violation for Clausius statement, automatically we get there also a violation of Kelvin-Planck statement. The reverse is also true. If there is a violation of Kelvin-Planck statement, automatically there will be a violation for Clausius statement. Let us take this very simple device in which we are again considering a source whose temperature is T1, a sink whose temperature is T2, and in this case you see there is a system. And for this diagram, look at this diagram very critically. You see that if we think it is a reversed heat engine, so we are taking heat Q2 from the sink and delivered it to the source Q2 with the help of some work, that is W. But this work is coming out as an output work from engine, and in this engine, that direct heat engine Q1 is the heat taking from the source. So there is a violation for the Kelvin-Planck statement, but from this figure you see that as such there is no violation for the Clausius statement. But when you think of this combined system, then we will realize that if there is a violation of Kelvin-Planck statement, automatically there will be a violation for the Clausius statement. Here you see that from this direct heat engine we write the expression for first law of thermodynamics, that is W is equal to Q1, and Q3 for the reversed heat engine. If we write down the expression for the first law of thermodynamics, that is Q3 is equal to W plus Q2, but W is equal to Q1, so Q3 is equal to Q1 plus Q2. So Q3 minus Q1 is equal to Q2. That means the heat is being supplied from the sink Q2 will be equal to the heat going in to the source whose temperature is T1, that is Q3 minus Q1. So it is the violation of the Clausius statement that for any thermodynamic cycle it is impossible to transfer heat from a low temperature region to the high temperature region without doing some external work. So we had discussed, if there is a violation for Kelvin-Planck statement, automatically there will be a violation for Clausius statement, and if there is a violation for Clausius statement, automatically there will be a violation of Kelvin-Planck statement. So these two statements will go hand to hand together. Here let us take a very simple example, because these examples are very, very important from the tournament examination point of view. So we have taken a very simple example that a heat engine operates between 527 degrees centigrade and 27 degrees centigrade. Find its efficiency if the engine is reversible and the engine is irreversible. For a reversible engine, the expression for efficiency is equal to W by Q1 is equal to 1 minus Q2 by Q1. And finally we get for a reversible engine, efficiency is equal to 1 minus T2 by T1. My dear friend, please be careful while putting the value of T1 and T2. These are in the Kelvin scale. So the temperature which is given in Celsius scale, you have to convert into Kelvin scale by adding 273. So the temperature of the sink is given as 27 degree is equal to 300 Kelvin, and the temperature of the source is given as 527 degrees centigrade, comes out to be 800 Kelvin. If we add 273 along with 527, the result will come out as 800 Kelvin. So finally, the expression for efficiency, we will get 0.625 multiplied by 100, that is 62.5%. But this efficiency value for efficiency will be applicable for reversible engine. Obviously, for a irreversible engine, the efficiency will be less than the efficiency of a reversible engine. There is a very interesting problem, that is, a reversible heat engine is operating between minus 13 degrees centigrade and 37 degrees centigrade. Here the temperature of sink is given as minus 13 degrees centigrade and the temperature of source is given as 37 degrees centigrade. Find its COP as heat pump and refrigerator. First of all, we consider the coefficient of performance for refrigerator. That is equal to, finally we get the coefficient of refrigerator, that is equal to T1 by T2 minus T1. Again, we have to convert the temperature into Kelvin scale. So 273 plus 37 degrees centigrade, that comes out to be 260, and that here we have to convert this temperature which is given in Celsius scale, Celsius unit, into Kelvin unit. So we have to simply add 273 plus with minus 13 degree to convert it into Kelvin scale. Finally, we get the COP of a refrigerant is equal to 5.2. But while calculating COP of a heat pump, simply add 1 with the COP of the refrigerator. So COP of heat pump will be equal to 5.2 plus 1, that is 6.2. Now, reversible heat engine. A heat engine having heat interactions with two different temperature reservoirs is said to be reversible if its efficiency while operating as a direct heat engine is equal to the reciprocal of its coefficient of performance when it works as a heat pump between the same two temperature. We have got the expression for the efficiency of a direct heat engine, and if it is for reversible heat engine, we have already got the expression for efficiency. We have also got the expression for COP of a heat pump. So for a reversible heat engine, its efficiency will be equal to the reciprocal of its coefficient of performance when it works as a heat pump between the same two temperature. You can verify with the results which we have already discussed with the efficiency of heat engine and the COP of a heat pump. Now let us talk about reversible process and irreversible process. A process is said to be reversible if after the process is complete, means can be found to restore the system and all parts of the surrounding to the states they were in at the start of the process. But in reality, most of the processes are irreversible, and only for a mathematical model we can think of reversible process. And in practice, whatever the process we can think of, like heat transfer between two definite temperature, or cooling of hot milk on an environment, or burning of coal, or anything, any process, these are all irreversible process. But in thermodynamic system, let us first find out what are the causes for irreversibility. That is friction, solid or fluid, unresisted expansion, heat transfer with finite temperature difference, and mixing, etc. These are the causes for making a process irreversible. And our basic aim is to reduce these factors which is making this process irreversible, so that we will be very nearer to the reversible process. See, one very important point we must discuss, that is internal and external reversibility. During a given process, the factors that make the process irreversible may exist either only in the system or only in the surrounding, because when you think of universe, that universe is composed of system, and outside the system boundary is known as surrounding. So the factors which are responsible for making the system irreversible, they may exist either within the system or surrounding. If they are the factors which are making the system irreversible, if they exist within the system, then we can say the whole system is internally irreversible but externally reversible. But if the factors which are responsible for making the process irreversible, if they exist in the surrounding, then we can say the whole system is externally irreversible but internally reversible. And here let us discuss one very important point, that a reversible heat engine operating between two reservoirs at T1 and T2 has an efficiency of 70%. A manufacturer of heat engine claims that he has designed an engine which, when operating between the above two temperature, develops 80 kilojoule work when supplied with 100 kilojoule of heat from the reservoir T1. Evaluate the validity of his claim. Here you see that in this problem it is given that for the reversible case the efficiency is 70%, but the manufacturer claims that he is getting output 80 kilojoule with input 100 kilojoule. So if we think of the definition of efficiency, that is output by input, as per the manufacturer's claim, the efficiency is 0.8, that is 80%. But for any engine, the efficiency cannot be greater than the efficiency of the reversible engine. Obviously the manufacturer's claim is not valid. Now time is very short, we have to wind up our classes, today's discussions. So very quickly I will go for the Clausius inequality statement. Statement 1, it says that when a system executes a cyclic process, the integral around the cycle of del Q by T is less than or equal to 0. This is for the cyclic process, and this is known as Clausius inequality statement. And for a reversible process, that is del Q by T, and if we take the integral of del Q by T for a reversible process is equal to 0. But for statement 3, if we think of when for the case in which when a system undergoes a change of state, the value of integral is independent of the path between the two states, and it all depends upon the two state points 1 and 2. So we get a value if we take the integral of del Q by T, and this value is nothing but change in entropy. So in the next class we will talk about the very important topic, that is entropy. Entropy is defined as the randomness of a system. So in the next class we will discuss about the entropy. So here you see that entropy S of a system is a property whose change between two states 1 and 2 is delta S is equal to integral del Q by R, lower limit is 1, upper limit is 2. And here the change in entropy ds is equal to del Q by T. So in our next class we will definitely take up this topic, entropy. So for today let us finish our discussion here itself. Thank you very much.